Good morning, ladies and gentlemen. I'm Jenny Bashford. I am the Knowledge Transfer Executive with AHDB Potatoes, and I'm delighted to welcome you here this morning to the first of the seminar sessions today. This is the interactive soils session, and it's been my pleasure and privilege to be able to work with the two gentlemen that are going to speak to you this morning, bringing you this session about, and basically we're asking the questions, what do soils do for us? Now, these two gentlemen don't really need any introduction, but I did it poorly yesterday, so I'm going to try and do it better today. We have Mark Stalham from NIAB-CUF, and we have Blair McKenzie from the Hutton Institute. We've got a lot to get through today, so without further ado, I shall hand over to Blair. And we'll have 5 minutes, hopefully, for questions at the end. But over to you, Blair.
Thanks, Jenny. Thank you all. Some familiar faces, some I don't know. What we basically want to cover a few things today, to think about the functions of soil. And obviously, a key function is to produce a potato crop, but all the things we need to do to deliver that potato crop. And as part of that producing a potato crop, there's a concern about whether we're risking compaction of the soil, how deep and what operational depths we need to do to produce that, to think about the consistency of the soil, how soil behaviour changes as a function of water content, having got that behaviour, how stable the soils are, not in terms of deformation as a result of traffic or tillage, but how stable they are in water. And hopefully we can think about that stability and then think about drawing a few simple conclusions from that. Thank you. So the diagram there is to think about getting a few terms right. And it's always, soils is one thing that everyone talks about, but we need to make sure we've got the right terminology. So for me, texture is simple. Texture is the amount of sand, silt and clay in the soil, whereas structure is the arrangement of those particles. And in an ideal case, we have those clay particles, silt particles, combining together, driven by the chemistry, the calcium, magnesium and these sort of things, to form microscopic microaggregates. And those microaggregates build together by mucilage from roots, from bacteria, to form slightly bigger and bigger and bigger units. So we end up with an aggregated soil that clods or peds as we move up. So there's the structural unit for me is an aggregate, is a lump of soil, and that you can find those naturally in soil. And we're asking the soil, that structure, to deliver a number of things. It's got to allow roots to anchor, it's got to allow water to drain through it, so we need different sizes of pores, so there'll be different pore sizes between those different sizes of units, and those pore sizes will be changed by the soil biology, by root growing through them, or by earthworms burrowing through them. We want the soil to retain water, we want air to get to the roots, because potato roots or wheat roots or barley roots are all living cells and they need oxygen. So we've got to get oxygen to the plant roots for the plant roots to function. And we've got to obviously have the soil releasing nutrients and holding enough nutrients and then releasing it at the right times. And then we want to think, as I've said, the final point will be to think about the stability of any structural units that we have. So thanks, Jenny. So this is my model diagram of a potato bed, if you like. And if we start at the soil surface, this is to think about all the things we're expecting the soil to deliver to produce a potato crop. So we want the surface soil to allow air in, to allow water in, but not to crack, because if we get big cracks through it, we get light in, we get greening and all the problems with that. So we need a stable, soft soil at the surface that will let all these transfers of fluids go on. If we move down into the main bed of the main section of the potato bed, we want the soil soft enough that the tuber can expand and not be deformed in the process. We want roots to be able to elongate easily and grow through that soil and explore and take up all the water and nutrients. We want that bit of the bed to store water and to release water so it doesn't get waterlogged. And we want it to hold air. If we move down to the base of the bed, we still want to be able to get roots down. If we've irrigated, we want water to be there so the roots can get it. So we want soft soil, stable soil, different parts, and then all on top of that, or below that in fact, we need to be able to support the weight of the machines, because you'll be putting different types of tractors, harvesters, trailers, all sorts of machinery on it. So we want the soil strong enough to be able to support that weight. So we're actually asking, for me, we're asking the soil to deliver an awful lot, to do all those different things. And a number of those things depend on the strength properties of the soil. Is the soil soft enough or is it too hard? So, just one more slide, yeah. Of course, the other thing we need is after the potato crop, we need to be able to grow another crop, because potatoes are grown in rotation. Every crop's grown in rotation. And so we've got to be able to finish off and have the soil to be easily got to a condition where we can plant the next crop. You can't look at the crop in isolation. So we're expecting the soil to be still viable and still, it's not a one-off exercise. We produce a potato crop and then go away for, we've got to do something with the soil the next year and the year after. So we've got to make sure that we can get the soil back into a usable condition for grass or for barley or for whatever we're going to put in. And that's another function of the soil, that we can get it back into the condition for the next crop. Thanks, Jenny. So just briefly, I've mentioned strength or hardness and softness of soil a few times. And there are lots of different ways of thinking about the strength of soil. Mark will talk a little bit more properly about penetrometers, pushing a needle into soil and thinking about how easy it is for a needle, which is analogous to a root, to penetrate soil. But there are other ways we need to think about the strength of soil. Sorry, and penetrometers can be different sizes. You can be right down at the 1 millimetre diameter scale or up to huge engineering type penetrometers. But the other ways we need to think about the strength of the material, for example, if we're worried about the soil surface crusting, we could think about this case here where we have a surface crust and we could measure the strength and how easy that crust will break up. The other one is we can take lumps of our aggregates of soil and squash them and crush them and see how easily they break apart. There are lots of different material properties of soil that we need to think about if we're going to manage those soils. So Mark, I think, will now take over for a little while and talk a bit more about penetrometers and what they really mean.
Yeah, thanks, Blair. You know, I'm the glamorous assistant that does all the practical work for part of this. So what we're going to do now is, when I put up numbers, I think the audience I've got here recognise a lot of faces, people have been around. Still, the numbers might not mean a lot to people. So when I talk about numbers, I'm going to translate it into green, amber and red. And red is the area we need to avoid. And so what you're going to see now is that the film camera is going to come down and pan into basically the same soil that we dug out from NIAB-CUF. I say we, my technician went and dug up half the field, brought it back to me. We've actually artificially dried the soil to get a dry soil that you might experience following an extremely dry summer grown under cereal. So same soil type, it's a sandy clay loam stroke sandy loam, about 18% clay content, but it will behave plastically. In other words, we can produce this soil here in the wet pots. I can roll a thread down to a diameter of about 3 millimetres. That's a definition of a plastic limit. So if we're running steel machinery through this, we can deform it plastically and we can create compaction. We're going to talk about compaction in different measures in terms of a loading compaction and an effect of cultivation having effect on crops. So two different types. We're measuring soil strength. Blair talks about hardness a lot, and when we talk together, I often move more towards his scientific terms. So when I talk about strength and hardness, that's really the same term. Technically, they're not, but they are for this purpose. Soil strength, other than a sand on a beach, imagine a beach, the dunes at the back are really weak because they're dry. A sand nearer the beach, when the tide comes in, gets stronger. Every other soil, okay, gets weaker the wetter it gets. So the sand is one of those things that's a little bit out everywhere else. Think about that. What we've got here is a soil that's wet from field capacity, dug last Friday, and it's been protected in plastic bags, so it's still at that. We've got a soil that I've tried to repack to as my technician Ben dug out of the field. And I'm just going to stick a penetrometer in it and give you an idea of how hard this soil actually is. I'm pushing down at the rate through the soil of about 2 centimetres per second, and we've actually got no movement on that black needle. We're right at the bottom of the green. What I've done now is repack this soil to the equivalent that you'll start to see in a moment when Blair talks about another slide, of a tractor running over the surface. A small tractor, albeit, so it's packed, but it's packed at field capacity moisture content. So I'm going to do exactly the same thing. As long as I don't go in the hole that I dug yesterday, I can go down, and I'm beginning to go through. The needle is just beginning to move as I go through the soil, but the green is right at the bottom of potential root growth rates. We'd expect in here the crop to be growing its roots at about somewhere in the region of 1.5 centimetres per day. Loose soil, easy to go through. Packed soil, when it's wet, still goes through. Now I've got basically the same packing density, but the soil's dry, and it's quite hard to repack a dry soil. So what we've got here is the loose soil, which I'm going to push through. And as I go through it, it's dry, and again, we're beginning to get a movement. As I go through the soil, it's getting harder and harder. Now, when I did this on Friday, just to check it worked, I could go right to the base of this pot with very little force. It was just registering in the middle of the green. What's happened is, my colleague drove me up here the other day, and the shaking around in the back of this van has packed those dry particles very nicely in there, and now I'm getting a higher reading. So if I now go to the dry packed, this is the one I really packed quite tightly under a dry condition, and as I go through, I'm getting up into the red. Those are the same soil types, just at different moisture contents. If we work our soil in the spring, we work it largely nearer the wet end. So when I stick my penetrometer in, following you guys going and do a various series of cultivation operations, I largely experience the wet soil. So compaction that you create is often hard for me to find. You've got to look for it very carefully. You get small readings on a needle. The time to look at it is to come back in July, and if the soil is dried out, you'll find massive differences in the depths where you've cultivated. So use the tool correctly. Moisture content determines soil strength, but the right time of year is to do it when it's in that dry zone if you want to compare the effects of trafficking or different cultivation machinery. Okay? Right. One more. Yeah, Johnny. Okay. Right, so these are some data. It shows really how old I am because I started this work back in 1992. We used a different penetrometer, but we've calibrated this one to be the same. And what I've put on there is the area of green correlates with the area of green on this penetrometer. The area of yellow, same, and red. The top end of the red bar is basically the point when we get no further root extension. We've stopped root growth in potatoes. What it means is that if you grow a variety that has a potential rooting zone of about 70 centimetres, that's the 100% potential. What we're showing there is, if we look at previous data back, sort of 20 odd years ago, we find that a lot of crops actually don't make 100% of potential because we're restricting their root growth by having up to 3 megapascals of soil hardness in our profile. Well, if we look more importantly at the two aspects of more recent data, which are not my data, they're collected under a protocol I designed for a company. There's about 270 odd fields here on the left, and there's about 600 on the right. What we find is two things. The first thing is we seem to be getting deeper compaction. Our crops are only utilising 90% of the potential volume of rooting. We're getting harder soils at depth, bigger tractors, which we'll talk about very shortly. The other thing is we're getting better at cultivating soil looser in that zone. So the 36 and the 43 relate to the centimetres depth of easily rootable soil. Bigger tractors, deeper working, so we've got loose soil in the upper profiles, but we've got harder soil, probably as a consequence of the bigger tractors that we use in all our operations, compacting the subsoil. So that's a sort of scare message, where we're going. We might end up in 20 years where we're only using 80% of the potential. Okay. So what Blair's going to do now is just run through a scenario that I've actually put up here. Blair's just going to run something. It's a model called Tyranimo. You've got the link there. It's in your handouts. Please go and have a play, inverted commas. It's giving you some indications of the risk of damage. Again, ignore the numbers. Look at the colours. We should not be in the red. So, Blair, do you want to run through the example?
Thanks, Mark. You can keep looking at the screen. Things should come up fairly nicely on the screen, hopefully. And all the textbooks say don't work with don't do presentations with children or animals because things will go wrong. The one I'd add to it is don't do presentations with computer models in live time because things can go wrong. But we have the Tyrannomo model, which is freely available. The links are there. And we'll just take a quick example. So we might get rid of the slurry spreader, if that works. Hopefully it's thinking about it. And we'll try again. Let's see if we can pick a different tractor. It's thinking about it this time.
It worked yesterday.
It worked yesterday.
Right. I think can we get? I think we might have to reload that, Mark.
Okay.
And so if you go on to talk about the next bit,
Yeah, do you want to?
I'll give it another try.
See where it goes. Okay.
Give it another try now. So that's the introductory page. If you come to it, and we're picking on the Europeans.
Please go to global, unless you're Danish, because Danish is really hard to understand.
Now we're working. And we'll pick a standard 330 horsepower standard tractor. Now you can spend a lot of time, you can change tyre pressures, change all these sorts of things, but we'll pick a standard tractor and we'll describe the site, and we're going to pick, for example, a clay loam, and in the first example we'll pick a dry soil. And then all we need to do is to go to the results of the profile, click on that, and so this would be a standard 330 horsepower tractor, and you can change the tyre pressures and all that sort of thing. And you've got, for the front axle and the rear axle, the black line shows the compaction risk under those tyres, under that tractor. So if the soil's dry, for that sort of standard tractor, we're not really concerned about the compaction risk. But if we went to go back and describe the site and picked the soil as wet, as it might be if we were trying to go on to the soil in March, even though it's not a big tractor and it's not pulling any implements, and do the same sort of story, we can see that we end up with the risk of compaction and the scales on the left-hand side, so that compaction risk is not just at the surface, but can go down to 30 or 40 or even 50 centimetres under the real wheel. So it's a tool, it's freely available to think about the risk of compaction and what the consequences of driving a single normal tractor, or you can vary the tractor. There's other trailers, tyre types, all those sort of things that you can use and play around with and see what the risk of compaction and the risk of the depth of compaction that you can do by working wet soils. So thanks for that. We'll go back to...
Right, okay, so Blair's talked about one of the two components of compaction that largely affect farming, which is a loading force. What I'm going to talk about now is the other one where we can create compaction, which is running steel machinery through soils at various depths with different water contents. Now, again, you know, a lot of data here. Okay, just take what I take about the pictures, ignore the graphs on the right, because there'll be a slide coming up presenting a summary of that. What we've got is basically variable fields where the electrical conductance scan that we've taken at the beginning of the season prior to doing some experiments on cultivation depth, we've got marked differences. The yellow areas are lighter soil, lower water holding capacity, which is what the scans are showing. The blue areas, as you can see by the clay content, are heavier. They're sandy clay loam soils. And what we've done is basically taken measurements of soil water content down the profile on the day we actually did all the cultivations for planting. And very simply, there isn't sufficient clay content and sufficient water in the sandy loam red areas to deform the soil plastically at the depth we wanted to cultivate at. So typically 30 centimetres, the soil is too dry, whereas the blue areas indicated on the right-hand side of the diagram are 3 vertical black arrows. That vertical black arrow indicates the depth where the plastic limit was exceeded in the sandy clay loam blue areas. So if we go to the next slide, what we see is a summary of that. these were all taken in potato beds formed prior to destoning, so I converted them back to a depth from a flat soil surface, the one in the red ring. What you can see is that is the critical depth for avoiding compaction from plastic deformation in a sandy clay loam on this site in 2012 to 2014. Now, these 3 fields are under the same rotational system, they're under the same management system, and they're not very far. They're either adjacent or 2 fields distant to one another. So the same soil series, everything's the same, but over 3 years, what you've got is about a 5 centimetre difference in your critical depth of cultivation. So if we move forward to the next slide, what we've actually done is taken one of those fields and actually do a lot more work than people think. Actually, we've decided if we set the optimum depth based on water content, clay content, organic matter, and bulk density, we can actually produce a map from the water content of the field that tells us how deep we should be cultivating in each of the different zones. Now, this is smart. You know, I've done that for 2 fields. That's one. That takes about a day of analysis to do that. And when somebody's out with a tool, like you can see at the bottom there, they don't really want to wait a day for me to tell them how deep they need to be. So what we did was, you can see the company. They're both around here. They produced a box which relates the scan colours to depth of bed produced, and then the destoner comes through and takes the whole bed out and produces things. So the technology's there. It works a treat. The 2 companies have worked out brilliantly. In the first year of the project, I didn't have data to back it up, and as a scientist, we still need to take more data to be comfortable to produce that sort of mapping. With GPS, we can actually utilise that really effectively. So that is a sort of scare story. Have we got enough soil to plant potatoes when we've only got 24 centimetres of workable soil without the risk of compaction? Okay, well, a lot of measurements go into that. Can you do something visually? This is a grower in the audience, 2014, working along. We are now in the optimum, excuse me if you've had a few beers last night, it does get a bit wobbly, but you're now in the optimum depth for yield and quality in this field, and you can see the marked change in the amount of debris, i.e. clods in this case, coming out the side of the machine. If you work a machine down in a fairly consistent soil type, you can actually find that inflection point, the point when you start to drop more out the side. You'll still have sufficient soil in the bed to plant potatoes, but if you go any deeper, you'll just produce more clod and your bed really won't get any deeper. So that's sort of visual marker. If we go to the next slide, it shows you basically here, it's not really the type of machine you use. You know, the Tillestar's available, you know, downstairs to look at, but you can see the speed that people are pulling off clods on the right-hand side, and that's just an indication of the variation. Very little clods. It's not the machine, it's the depth. The pitch of the web, there's gaps between stars, whether you bed till or not, it's largely the depth you work at. We work our soils too deep for clod avoidance. That's a take-home message, and this is more of a pictorial study. I can show you the data in terms of the weight of clods and the depth, but that's more visual in terms of that. So think about depth. We all think about machine, changing pitches, changing the type of machine, the combination of machines. This is what's turned out. Work too deeply, the clodding content increases. And that's what you're trying to avoid on the harvester. Okay, so Blair talked about, you know, the effect of loading forces. I'm talking about the effect of restricting potential soil exploitation by roots. So his second slide was about what we want. In this case, Blair's subsoil layer is heavily influenced by what we've done as cultivations. Now, clearly the crop on the left, the 8 rows to this side, are different to the 8 rows to the right. Now, what's caused that? And I've been showing it's 2006 data. You wouldn't want to see this now because it's actually now high-rise blocks, and there's a school right on the right-hand side here. It's all been developed for housing for the university. But if we now click onto the next one, you'll see what's actually happened. We cultivated, 2006, the driest spring we'd had since 1996. And the conditions were about as perfect as we ever get. We were able to have an optimum depth, a critical depth of cultivation that exceeded 32 centimetres. So we could produce that soil without any damage whatsoever. It was in a good state. We irrigated the right-hand 8 rows in terms of this replicate. the night before we cultivated. We allowed it to drain, and that soil was cultivated at field capacity. Yes, it's extreme, but you can see the results of having that extreme treatment. Both of those crops, you don't know when this is 30th of June, this picture, in 2006. That crop on the right is clearly a long way behind. Now, what you haven't seen is this crop on the left got to full crop cover 3 weeks earlier than the 30th of June. And this one eventually did get to full ground cover in some of the treatments, but it was right until August rather than the beginning of June. So if we go to the next one, you say, well, yeah, maybe it was shorter water. This is the highlight of this slide and why I keep producing it. It's good data from years ago. It took a lot of work to do. The one on the left and the one on the right, you've seen the one on the left as a picture. What it had was no water applied by the time this picture was taken, the 30th of June. The one on the right had 3 doses, and you can see it actually had a dose the day before because you've got standing water in the furrows there, and the silt content that's been washed off. I don't think you can see a lot of difference to response to 65 millimetres of water there. On top of that, you've also got in these they've got main plots of irrigation times cultivation. You've got subplots, which are basically 6-7 metres long, which are showing high nitrogen for Maris piper, 300 kilos, 200 at the back, and I think you can see on the right-hand side the naught is a bit less. But the response to this was we did not reach the optimum in compacted treatments at 300 kilos of N. If you just go back, Jenny, to the previous slide, can you go back? Yeah, that one, the crop on the left, the optimum for Maris piper in that field, in nitrogen regime, was somewhere between 0 and 100 if we didn't have soil compaction. And we didn't have an optimum on the other side. It might have been 400 or 500 kilos. Go forward again. And when you take soil samples at the end of the season, we find the crop on the right, okay, had 300 kilos applied, and about 250 kilos of that was still in the soil at the end of the season. So the root system was affected by the cultivation regime because we created a root zone that didn't go beyond 40 centimetres deep. And the other crop on the left was over 1 metre when we dug it in an open day in August. Okay. Right, okay, so what happens? Well, in cultivation, if we do it incorrectly in terms of depth, what we've got here is a heavy soil, which I could present as a scientist and say, look at the difference, 17 tonnes per hectare caused by a variation from cultivating at 25 centimetres, that's shallow, right down to deep, which is 50 centimetres. That's really excessive. But look at the differences between the shallow and the commercial. They're still quite large. Even on the light, sandy soils, we're still getting a directional effect. Now, if we go through to the next slide, the summary of 16 experiments, I've got another 4, which I can add into this from this year. The red area is the commercial depth that the growers were cultivating, and the 2 depths shallower than that were actually our sort of treatments which we thought could we get to a different optima by cultivating shallower. If you look at that, the shallowest treatment is significantly higher yield than the red commercial practice in the field. Significantly, in other words, statistically from 16 experiments. That tells me we've got something that we can do less, we can work soil less, we can work shallower, we can save fuel, we can save labour, and we get an increase in yield. And I'll show you the economics in a bit. Okay. Right, Blair.
Thanks, Mark. So Mark's talked a lot about strength. He's talked about penetrometers. He's talked about soil being plastic. And what I now want to think about is thinking about cultivation. And if we want to cultivate a soil, we want to get the soil to have the right proportions of particles of the right size, aggregates that are small enough to allow for roots to grow through, for tubers to expand through. So we've got to take the soil and deform it with a tillage implement to break it up, to expose new surfaces. We don't want it to smear, to be plastic. We want it to fracture and be friable. So we want to think about strength and cultivation. So I've introduced some terms here. Mark's defined the plastic limit. This is soil wetness. There's no numbers on here because it will vary for each soil, and we've got the volume of soil up the right-hand axis. So if we think about soil, we don't want to cultivate a soil if it's wetter than the plastic limit. If we get a soil very, very wet, we can get to the stage where the soil will behave as a liquid, as it does, for example, in the case of a landslide. And obviously, we don't want to think about those sort of things. But as we go drier from the plastic limit, the soil will eventually get to a point where the volume won't change and the soil becomes increasingly hard. It becomes stronger, becomes harder to fracture and to break up and to create new surfaces that will release nutrients. So if we're thinking about trying to cultivate a soil, to create a seed bed, to create a bed for potatoes, we don't want to go too far that way because the soil gets hard. We don't want to go that way at all. We don't want to be wetter than the plastic limit. So we're wanting to do our cultivations just that little bit drier than the plastic limit. So the soil will deform, not by smearing, but by breaking into new, smaller units. So how do we do that? I was going to bring in a tractor and bring a whole tub of soil and do, but they wouldn't let me bring one in here. So I've got to try and think about ways to put energy into soil. And that's what you do. When you're cultivating a soil, you're putting energy in. You're buying diesel, which is energy, and you're pulling an implement through. So you're putting that diesel as energy into the soil to get it to break up. So we want to get soil to break up. How can I do that? So I need a way to put energy into soil. My basic physics tells me that if I take a lump of soil and hold it up and I drop it, I know what the energy state is, don't I? I know the height, and I can put the energy into that lump of soil by dropping it. Now this soil, and sod's law, one of them won't work, but this is a lump of soil. It's from Mid-Pillmore, one of the sites up at Dundee, and if I drop that, it doesn't break apart. That soil was hard. It was too dry, and putting that bit of energy in didn't create the new surfaces, didn't break the soil into the sorts of particle sizes we want. If I take a soil, and again, same soil, hopefully just about, no, it's falling off, just drier than the plastic limit, and I drop it from the same height, we'll see what happens. We've created a whole lot of new surface. We've broken it apart. And cultivation is simply putting energy in the soil to get it to break apart, to fracture along pre-existing cracks, those cracks and pore spaces that are in between those microaggregates. Now, we've taken the soil, we've got it at the right water content, and we can see for the same energy input, same clod size, same height drop, same gravity, we put the same amount of energy, we've got a very different response to break up of the soil.
Blair, can I just make you aware that we are on time?
Okay, right, I'll be very quick then. If I take a different soil from further along, about 2 miles away, with a lot of clay in it, and I drop it, even though it's at the right water content, nothing happens. That soil's got so much more clay, it needs a lot of drops. And that's simply saying to cultivate a clay soil will take a lot more energy. So I could either drop that soil, cultivate it lots of times and drop it lots of times, or I could work it faster. So we can think about putting energy into soil, and we think about having the soil at the right water status to do that. So get on to Mark. Yep.
Okay, now Blair's quite unsubtle. He can vary how high he drops the clod from. Machinery that we operate, particularly rotary machinery and sieving machinery, is very, very aggressive at putting that energy input. It breaks down the big ones slowly. It breaks the small particles down more rapidly than we want, and the bits in the middle largely stay the same. So what I've shown here is I've got the camera to focus on basically 3 soil types with a range of aggregate sizes that we see commonly in potato ridges. So we've dried these soils. We've got a peat soil, a clay soil, and a silt soil. And we've dried them, and I've selected 6 to 10 millimetre aggregate sizes, and I'm going to drop them into water repeatedly for the next 3 minutes. So if I do that, and I'll explain what we're doing. But if you just focus on there, we've got the silt. I'm just going to drop that down. And what we're doing now is simulating wetting, drying, wetting, drying. As it gets dunked in and out of water, it's raindrops, irrigation impact on the soil. How stable these soils are makes a big difference to how we perform in terms of potato production. So we're dropping them in. What I've got is the silt soil I've divided down into another fraction smaller, 2 to 6. And then what I've got when Blair talked about textural units, less than 2 millimetres is in the area where we start getting individual sand grains So that sort of size, less than 2 millimetres. So very fine, fine, and a little bit coarser. So we've got this as a mixture ridge. That's going to dunk up and down. If we go to the next slide, which is the machine, go to the next one. Okay, the next one. Blair will talk about this, and then I'll come back while it's doing.
I'm conscious of time, but these are some data from, Mark's got a blue machine, I had a green one, which was sure the photo of, but it's from data from our Centre for Sustainable Cropping at Balruddery, where we have a convention, where we have a 6-year rotation, which includes potatoes in the rotation, and we've got, the fields are split into conventional management and a sustainable management. And the sustainable management through every other crop than potatoes gets no cultivation, or obviously it's cultivated through potatoes, but it has additional organic matter. The local compost is applied, so we've built up the organic material in the soil. And we can simply see that these are the proportions of the soil that is stable for different depths under the sustainable management. And we can see where we've built up the organic matter, not surprisingly, the particles, the units that Mark's talking about, hold together better. We get more, in this case, 2 millimetre size. You can vary the sizes of the sieves. We've picked one for 2 millimetres, and you can see under the sustainable management where we've increased the organic material in the soil, we've got the chemistry right and got the organic matter build up, that we see more stable units that won't slake and break apart when we get rain, and so we won't have the capping on the surface of our potato beds.
So what does this mean? If you take basically a house brick size core of soil from a potato ridge, immediately the crop has been planted. So the picture at the top, you can see some planted rows to the left of the distoner. We take a core then, and what you've got then is the green bars in both of those two soil types there are the beginning of season. We do it again the day prior to harvest, and you've got the red bars. What we find is that soil density increases during the season in the ridge. The ridges consolidate and they slump. Slumping is sort of due to rainfall wetting patterns. Consolidation is natural settling and so on over the season. What we've got there is 2 points. Clearly the soil on the right-hand side, the difference between the green and the red bars is a lot larger than the stable clay soil that you can see at the top. The beds you can see on the left relate to the right-hand graph there at the bottom. They were bed-tilled. The machine actually went through the day after planting. What happened in 2012? It rained for 6 weeks. So that soil was incredibly unstable to the rainfall events that followed. The clay soil suffered the same rainfall, but actually remained much more stable. So what are we looking for? We want stability. We want bigger aggregates in our ridge. And this is really where the machine comes out. I'll take basically the clay soil, which was 6 to 10 millimetres in diameter before it went in. It's been dunked for a whole season. Look at the volume and look at how the PEDs have actually broken down. So that's the clay soil. If we take the peat soil, larger volume, less has gone through the sieve into the water below or down into the subsoil profile. The aggregates have broken down, but they're still visible. We take the silt soil and we drop that. A lot less volume, very little structure left, and as we work deeper down, we see basically even less, and we get to the soil, which is effectively gone. There's virtually nothing left in there. It has gone through the sieve. That's effectively what's happened. We want bigger aggregates. Don't be scared of big aggregates. They will break down during the course of the season to leave us with less at the end of the season. Okay, right. Okay, we'll skip through that one. It's just the next slide we want. So, you know, we talked about soil. Well, yeah, how does it affect my business? Well, there's a lot of data that's gone into this. I had Neil Cameron in the audience yesterday, and we spent an hour and a half beyond midnight 2 nights ago discussing the economics of this. And we've got some differences of opinion, but we're going to resolve this. But very simply, this is a simple system, but it works. If we take an example of a new machine purchased by you can see the type we've done there, 120 hectares grown. We've used the yields out of the predictive system from all those experiments I showed you. So what we've got there is a 56 hectare grower. Currently, that's an average levy grower area, would save £2,000 in money by cultivating 6 centimetres shallower on the destoning operation, and that's worth another £13,000 in extra revenue from the crop. But the little box down there is really crucial, and this is the thing. One take-home message above everything else is, when the going gets difficult, 1 to 2 centimetres shallower will gain you more depth and actually improve your yield than actually trying to go the same depth or trying to work soil deeper to achieve your seed beds. So that's where we got to at the moment. We've got a summary slide, but pretty much I'd rather spend the time, on questions, if any come from the floor.
Well, I think that's been a pretty amazing run through our soils and what we need to be thinking about. We've got time for very quick questions now. Does anybody have a burning question that they would like to ask either Mark or Blair?
I'll ask the question, which is, it comes out of Mullet Muppins last night, which is, we heard about X Factor. Please put your hands up if you actually watch Strictly Come Dancing. We're not going to get any questions. Let's go. Come on. A lot of people that probably watch it but don't admit to it. So
Yes.
Come on. Any questions? Yeah, one, Dennis. You watch it. Okay, fine. That's good. Okay.
Does anybody have any questions? May I ask you one then, if I may? What impact, if any, do you think organic matter has?
Well, Blair presented some data on that, and I'll follow Blair.
The comment is, we need to be careful what we mean by organic matter, because there's lots of, organic material just is anything that's plant derived, and there's different grades. Coal is organic matter, and I know adding coal to soil doesn't improve my soil. So we need to think not just about total organic matter, but the quality of the organic matter and the forms it's being added in, but increasing up to within reasons. I mean, peats are all organic matter, but in general, we're trying to make sure we don't decrease the organic matter concentrations in our soil.
Yeah, and Blair's a scientist. You come out, you pull something out of a literature review, and you say, somewhere in the literature, somebody wrote, and it's been widely quoted, that we need 3% organic carbon in our soil, which is about 1.8% organic matter. Sorry, the other way around, 1.8%, 3% organic matter in our soil. In East Anglia, where I surveyed soils, the average is 1.8. Yes, there's some soils up into the 4s, but most of them are below that level of criticality for stable soil structure. So we don't need to go to 10%, but another 1% would be remarkably beneficial. How do we achieve that? Well, hopefully in 4 years' time, Blair are sort of crossing our fingers that somebody will be sponsoring us to do that work, and we'll be able to give you the answer.
Thank you very much. We are unfortunate. Oh, we do have Tim, please do.
A sort of two-part question, really, Mark. Have you done any studies between Tilly Star and normal type de-stoners, and the difference between those? And have you done any studies between 1 bed and 3 bed? Because the 3 bed would have a much bigger power horse on the front, which would put more compaction into the soil.
Yes.
Have you done any work on those two?
Yes. Probably, Tim, by now, if you ask me any question along that line, we've got some data somewhere, because I know what your interests are, I know what other people's interests are. Whether it's scientific enough to present in front of Blair, no, but we've done studies. The tiller star, yes, versus de-stoner. And largely, there's no difference, except when you start working beyond the plastic limit or the critical depth. Then rotary implements, doesn't need to be tiller star on the label, but any rotary implement, think of a bed tiller, should not be working in that water content soil. As you come shallower, all machines become more similar, which is what I was saying. It's depth that's critical. When you use rotary machines as opposed to slicing machines, then there isn't that difference. Go beyond the critical depth, and the rotary implements are all bad. Doesn't matter what they are. So whatever colour they are. So that's the question. The other question, we have data on it, and it is scary, because the wider the machinery, the bigger the draft, the bigger the tractor. Blair talked about the compaction. What we are finding is, if you sample 3 sequential beds, you can definitely find, blind, just say you start anywhere in the field, where the towing tractor on the bed former was, despite de-stoning afterwards, because the tractor has put the compaction in deeper than the implement behind being towed. And that's a scare story, and it's part of another bit more funding work. We want to say, how severe is that in terms of root growth, and yield and quality and everything like that. So we've got it, we know it's there and it's more severe, which is why we're not getting 80 tonnes per hectare as a national average rather than 48. All these little things are adding up to reduce it, and some of them are quite scary. They're 3% and 4% yield losses. So yeah, if we can answer more of those questions and then say, is it better to go back to lighter tractors? Is it better to use wider equipment? No.
Can I just suggest, because I just know I don't want to hold the rest of the seminar programme up, but I know if you give us 5 minutes, because we just need to clear these things away, then both Mark and Blair will be available just outside in the knowledge zone. Is that all right with you, sir? I'm really sorry. Is that okay? Thank you very much. Can we show our appreciation for our speakers in the normal way?